Hey, Sarah. Here's the attendance form. So far, it's just you and me. I'm guessing you guys started talking about chapter 12 stuff yesterday.
Yeah, we started talking like permutations and some other probability stuff.
Sure. Yep. Okay. Pretty standard.
Hmm.
Wait a minute here to see. No. Wait a minute here for class start. Well, Luna. Going in a moment here. Out. Okay. Be nice if someone was here in person. Not that you two should necessarily be here in person, just that it always feels weird talking to an empty room. But I guess I could do that. So. Yeah, chapter 12. I've got some pens that are on their way out, so I might be switching pens a lot. Let me try on some. Let me try. Okay. Around the quarter. Lucky day. Sorry. So let's talk about the principles of counting. So we're in chapter 12. I guess I could let this pen has so much ink in it, though. It's so frustrating. You're kind of thing where you like lick the pen, like feels like it's supposed to make it like write better. Nope, surely does not. Like made it write worse. It's terrible. Okay. I guess you're done. I don't want you to be done though. So chapter 12, principles of counting. Specifically section 12.1. So we've got a couple different things we're going to talk about. Basically rules for how we sort of count the number of things that there are in a specific setup. By the way, please feel free to unmute yourself if you have a question, you want to ask it, or type something in the chat. But there's no one else in here, so you don't have to be like feeling weird about unmuting yourself. So let's talk about the multiplication principle. I'm really trying to make this pen work, but it feels like it doesn't want to work. Multiplication. Wow. Yeah, these pens. Weak. Find one that works, then we'll stick with it. So let's look at some example. That was the blue pen. So in planning your schedule for next quarter, which you've already registered for, I assume, there are 4 different stats 13 sections, 2 different, biosci 2B sections, 3 Chem 2A sections, and you don't want to take all science classes because you want to have some variety. There are 2 different music 10 sections. How many different ways can we make our schedule? Assuming none of the sections overlap with each other. So like choosing one thing doesn't eliminate something else. Which is an unrealistic assumption, but it's not the point. Let's see if I can find a pen that actually works. All right, we have some options over here. All right. So here's kind of the way we're thinking about this. You could either, so let's see, I've got 4 different stats 13 sections. So let's say I pick the first stats 13 section. After I pick that, then there are 2 different sections to pick for biosci. You have the first section or the second section. And then after I've made that choice, there are 3 choices for chemistry. So I can pick the first section or the second section or the third section. Same deal here. If I made that choice, I could do that, that, or that. Welcome, Swati. Hello. And then finally, after the chemistry choice, I could pick any 2 of the music choices. So I could pick the first music section here or here. And I don't want to write them all, but I could do that here or here or here or here or here or here. And then I could do the same thing here, right? I could do first section or second section, first section or second section, first section or second section. And then I could make the same list for all those things except for choosing the second section of stats 13. So I could do that and then the same sort of B1, B2, and then all the other choices. So let's see, let's count them up. There are 1. So I'm just looking at really every branch of this tree I've drawn. There's 1, 2, 3, 4. I really have to count all the different endpoints. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different possible schedules, just taking the first section of stats 1. And then there would be 12 more here if I to pick the second section, and 12 more for the third section, and 12 more for the fourth section. So it looks like there should be a total of 48 different sections or different schedules I could come up with, taking a stats class, a chem class, a bio class, and a music class. However, this is a lot more work than I wanted to calculate. And so what I could have done instead is I could have just multiplied all the things together, or the number of things. So I could have said the total number of possible schedules is just going to be the 4 different choices of stats section times the 2 different choices of bio section times the 3 different choices of chemistry section times the 2 different choices of music section. And 4 times 2 times 3 times 2 is 8 times 3 is 24 times 2 is 48. So that's kind of the idea at its very basic level, is that if you've got like a bunch of different choices to make to kind of see how many different combinations or possible outcomes you've got, often we have to multiplying all the different choices we've got together to get some total number of choices. Let's look at some more examples, but they're kind of all the same ideas. Like if you've got one choice for one thing and another thing, we just kind of multiply those numbers together to get the total number of possible outcomes or choices or schedules or whatever we're talking about. Do let me know if you have questions. Sarah, I hope you come back. So let's look at the next example. Again, they're going to feel pretty easy to start off with, but they're going to get hard. Let's say in a study of the effects of light and fertilizer on levels of plant growth, you are going to plan to study 5 different fertilizer levels and 3 different light levels. You also don't want to just use one plant for each combination of light and fertilizer, because maybe that plant's not right. Maybe you want to have some redundancy in your test. So we're going to use 4 plants for each light and fertilizer combination. How many plants do we need altogether? Well, let's see. We have the number of fertilizers, which is 5. The number of light levels, which is 3. Oops, random thing here, light. And then the number of plants for each combination, which is 4. Which makes sense if you think about it, right? If we have 5 fertilizers, each fertilizer has to have 3 different light levels. So you've got the fertilizer type 1, 3 different light levels. Fertilizer type 2, 3 different light levels. Fertilizer type 3, 3. So you're going to have 15 in all combinations. And then for each combination, we want 4 plants. So we're going to get 5 times 3 times 4, which is 60 plants we need. Question so far? Yes, you all can see. Classroom's very empty. No. Someone might show up later, though. Often people show up a little late. It's all right. Okay, so continuing on. One more example, just to kind of bring it home, of just the multiplication principle, which is really just you're multiplying all the possibilities together. Let's say, let's look at the following. The genome for HIV contains 9,749 nucleotides. So, and we'll talk more about this in just a second. So when we're talking about DNA nucleotides, we're thinking, right, the different possibilities are the A, C, T, and G. So how many different genomes are possible? Don't quote me on the biology part of this, except for very, very basic biology ideas. But here, the idea is basically we're saying, well, there are 4 possibilities in the first slot, A, C, T, or G. There are 4 possibilities in the second slot, A, C, T, or G. There are 4, right? It just, there's 4 all the way down to the last spot. and there are 9,749 slots. So our total is going to be 4 times 4 times 4 times 4, that many times. So we're going to get 4 to the 9,749 power, which is very, very large. Too large for a calculator typically. So again, multiplication before, just saying the number of possible things here, right? So one thing to think about when you're doing this multiplication principle is that basically what's happening in one slot isn't really having any effect, or effect is what I'm looking for, on what's happening in this other spot here, right? I just want to say, well, there's 4 possibilities here, there's 4 here, and they don't really have anything to do with each other. Just like in the previous problem, there were 5 choices of fertilizer and 3 choices of light, and picking one of these didn't mean we had to like do something different with our light choices. So that's the multiplication principle, very basically. Let's talk about permutations. Oh, I know what I was going to say though. So there are some basic, or what people consider basic, biology and other kind of stuff, assumptions they're going to make about what you know. So I have a handout. I've actually made physical copies of it. If you want to come by class sometime and grab a physical copy of my office, it's also on Canvas. It's the, let me actually show you on Canvas. So in fact, that'll be easier for you to see it if I show it to you on Canvas. So one sec, let me grab this thing real quick just so you all can see it, because I do think it's worth your while to see. Get logged into Canvas real quick. 1 second. Yeah. And again, if you want a color physical copy, I have a copies printed out in color. But you're also welcome to print out your own copy, or just look at it online. If you go to the modules and you scroll down, I think to the bottom, to the handouts, terminology for probability. People looking like I'm crazy, or I think I'm talking to the old one. If you look at this here, it's got some stuff that people kind of are going to assume you know. So some biology facts we're going to assume people know. I'm just going to read it from here since it's easier for me to look at my paper here and look over there. But the chromosomes appear in pairs in mammals, 1 paternal from the father, 1 maternal from the mother. There are 23 standard chromosome pairs in humans. That's some knowledge people are going to assume you use. Gene is the genetic material, DNA. So yeah, I don't feel like I need to read all through this, but it also talks about like how Punnett squares work, how blood types work, very kind of fairly basic things that people are going to assume you know how they work for just purposes of calculating probabilities. And then on the back side, scroll down further, there's all the stuff about card names and how poker hands work. So if you've never played poker or you've never played with cards, you might want to check that out. It is because there most likely will be examples using cards in this class. Not 100% sure, but most of the time it's a pretty standard go-to example that mathematicians use. So you should know that there are 52 cards in the deck. There are 4 different suits: clubs, hearts, spades, and diamonds. There are 2 different colors, black and red. There are 13 different ranks or values: ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. And there are 3 face cards in each suit. There's a jack, queen, and king in each suit. Some people talk about face cards specifically. And then they talk about also the different hands you can get in poker and how they are ranked. We'll definitely come back to this later on when we start talking about poker hands and calculating probabilities of getting certain poker hands, but it's something you should be aware of if you are not already. Some people are like, I was definitely playing cards with my stepdad when I was like 6, so I definitely knew all about poker because I was really interested in playing it. But some people don't ever play poker, and that's totally fine. Not everyone should play poker. So back to what we're doing here. We'll definitely come back to those things. They will come up as we go on. The second thing we're talking about is permutations. So what you should think of, oops, sorry, I should show you the paper again. Sorry. When someone says the word permutations, or when you think about permutations, what we really are thinking about is the number of possible arrangements of things. Or in other words, arrangements. That is, order matters. That is the typical kind of thing we always come back to when we're thinking about permutations, is that the order that things happen in, or the order that you see things in, That is something that we care about. Oftentimes people like, well, I'll go to this example first, but we'll talk about examples. So let's look at this example here. I was supposed to be numbering these. Oh well, I wasn't numbering them. This is example 4A. So you're at the library. Maybe you're down in the drop-in room, getting some help with math or chem or physics. And you see on the shelf, because you're bored and you're not doing anything, it's all right, that there are 4 different math books. There are 5 different chem books. They're all different. There are 6 different biology books. So 15 in total, 4 plus 5 plus 6, all on one shelf. So the first question we're interested in asking is, how many different possible ways, or you may think of this word better, instead of different ways, saying how many different possible orders can we arrange the books on the shelf in? Excuse me. So here's where we have to start thinking about choices. So typically when we've got like things we're putting in spots, we kind of like to write out all the spots as kind of blank spaces. Sorry, that wire went down the wrong way. So I've got 15 books. I've got 15 spots. We're assuming like the bookshelf is full. Like you're not like leaving empty spots. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15 spaces for our books. And so then we ask ourselves, and it doesn't really matter where you start, but we usually start from left to right. So in this first spot here, how many choices are there for the book that goes there? Well, we haven't placed any of the books yet, so I have 15 different books to choose from. So there are 15 choices for that first spot. But now that spot had something put in that, good language there, that I put something into that spot. I've used one of my books. And now for the next spot, there's only 14 possible choices of books left because I have picked one of them. So in my second spot, there are 14 choices. And then in my third spot, there are 13, and so on and so on. All the way down to, in my 13th spot, there are 3 choices. In my 14th spot, there were 2 choices. And after, when I get to the 15th spot, I've chosen every other book. There's only 1 book left. So there's only 1 choice for the last book there. So this number, which we typically don't want to write as 15 times 14 to 13 times 12, all that, we usually write this number as 15 factorial, which means there are exactly 15 times 14 times 13 times all the way down to 3 times 2 times 1 possible books. I don't know what that number is. We don't usually really care about actually finding it. If you plug it into a calculator, you get approximately 1.3 times 10 to the 12th. It's a pretty big number. There's a lot of different ways you could arrange 15 books. But just to expand on this idea of factorials a little more, I want everyone to make sure they're totally cool factorials because they're going to come up a lot in this section. So, for example, just so you know, right, when you're doing a factorial, 4 factorial just means you start at 4 and you multiply by all the smaller numbers until you get down to 1. So 4 factorial is 24. And 3 factorial is 3 times 2 times 1, which is 6. And 2 factorial is 2 times 1, which is 2. And 1 factorial is 1, which is 1. And I should let you all know, because it does come up, that 0 factorial is defined to be equal to 1. It's kind of funky, but it is something we need to be true. It's kind of similar to why we need something like 3 to the 0th power to equal 1. In this case, it's because of the additive law of exponents. We need 3 to the 0 times 3 squared to equal 3 to the 0 plus 2. But 3 to the 0 times 3 squared is 9, and 3 to the 0 plus 2 is also 3 squared, which is also 9. So the only way this works is if 3 to the 0 has to be equal to 1. For a similar reason, which we'll talk about maybe later today, but certainly next time, if not today, 0 factorial has to be defined to be equal to 1. Again, it doesn't come up too often, but it does come up occasionally, so just be aware of that. Most of your calculators, if you have a calculator, should have a factorial button. I'm curious if it's on the stupid phone calculator here. Let's see. I do. It is on the phone calculator, right? If you look right there, all right. If you do like 5 factorial, it's 120, which is 5 times 4 times 3 times 2. Or if you do, let's see what happens if we do 15 factorial. Oh wow, it actually gives us the whole thing. So it's let's million. It's 1,307,674,368,000. That's a pretty big number. There's something else I want to say. Oh, let's just double check. Let's see if we do 0 factorial. Oops, that's not the right thing, James. 0 factorial. Yep, gives us 1, as it should. So factorials, they're just a convenient way of writing a log of multiplication. Let's look at the second question for this one. What if we want to follow up with how many different ways can we arrange the books if all the books from each specific subject have to be next to each other? Meaning we have to have like all the math, then all the chem, then all the bio, or all the math, then all the bio, then all the chem, or the other ways we could do that. Well, so let's think of one way of doing it. Let's say we want to do all the math first, and then all the chem, and then all the bio. So I'll remind you from the previous problem, there were, you see that? That looks a little blurry. Let me unblur that. If anything looks wrong, by the way, let me know along the way. Like usually people in class are more vocal about that. I'm sorry. So there were 4 different math books. So if I want all the math books next to each other, I don't care what specific order they're in. So the number of ways I can arrange them is 4 choices for the first spot, 3 for the second spot, 2 for the third spot, and 1 for the fourth, or more specifically, 4 factorial. And then they were 5 different chemistry books. So there's going to be 5 factorial ways of ordering them. And then there were 6 different biology books. So there's going to be 6 factorial different ways of ordering them. However, nobody said the books had to specifically be math, chem, bio. Maybe they're math, bio, chem, or math, or not math, sorry, or chem, math, bio, or chem, bio, math, or bio, math, chem, or bio, chem, math. How many different ways are there of ordering the subjects, math, bio, and chem? I want someone to tell me in the chat. It's a number. It's a small number. It's a 1-digit number. How many different ways have I got here? Anybody? I feel like he's saying something. Wants us to respond. Yeah, totally. That's definitely right. Now, another way to think about that number, which is 6, right? 1, 2, 3, 4, 5, 6, is you could just take the 1, 2, 3 subjects and say, oh, there's going to be 3 factorial ways of permuting them or ordering them. So we could take this number and just multiply it by 3 factorial, the number of ways of ordering or arranging the 3 subjects. So our final answer would be 4 factorial times 5 factorial times 6 factorial times 3 factorial. Most of the time for these numbers, we don't really care if you actually find the actual value as long as you can express it decently well. Here, you could probably multiply this out and it wouldn't be too terrible. It would be 24, which is 4 factorial, times 120 times 720 times 6, which I don't know. We could calculate it, I suppose, if we really wanted to. Now I feel like I need to. Let's see, we've got 720 times 6 times 720 times 120 times 24. That's going to be 12,441,600. Not as many as if we can just put books anywhere we want willy-nilly, but certainly still a lot, right? But remember the other answer for putting books anywhere was, like, what was it, like 1.3 trillion. Quite a lot bigger than 12 million-ish. So permutations order matters. And so we have to count all the different ways we can order the things, which really, really starts to add up. Let's look at another example. If you all have questions along the way, don't hesitate to ask. So very generally, the number of arrangements or orderings, or whatever you want to call it, or permutations is kind of the most official math word for it. The number of arrangements or permutations of n objects is n factorial. Typically, we are thinking of, almost always, we're thinking of n as a positive integer, or at least a non-negative integer, right? You're never trying to arrange like 3.5 things or -2 things. It's always 5 things, or 6 things, or 0 things, or 10 things. So let's look at some more examples. How many ways can we arrange the letters in the word cats? Well, I've got 4 different letters, and there's 4 different spots that they can go in. So we could do it the long way, right? We could be like, okay, well, there's 4 slots. There's going to be 4 choices for the first slot, 3 choices for the second, 2 for the third, 1 for the last, which is 4 factorial. We can even start to write them out, right? But it's going to be kind of, writing out 24 things isn't that terrible, but it gets to be a little bit terrible, right? You could have, I'm going to start with, so typically, I should show you this because it is worthwhile to kind of have a good system for doing something like this, because sometimes it is necessary to write them out. But I usually like to start with keeping the leftmost things constant. So I would start with CATS, and then I'm leaving the first 2 things alone and switching the last 2 things. So CAST. And then I've got all the ways with C and A first. So then I would do CS, and then I would do AT and CSTA. And then I've done CA and CS, and I'm going to do CT and SA and CT and AS. I know they're not all words, but we just asked about how we can arrange the letters. And then we do the same sort of thing, except we would start with something other than C. So then we would do like ACTS or ACST or ASTC or ASCT or ATCS or ATSC. And so on and so on, right? We could do it with TASC, TACS, TCAS, TCSA. So I'm being very methodical here, right? I'm doing T something and then getting all the last things, and then I'm switching the next things. Then T, I've done A, I've done C, I need S, A, C, T, S, C, A. And then finally, I can do, let's see. I've got C, I've done A, I've done T, I need S. S, A, C, T, S, A, T, C. S, T, A, C, S, T, C, A. S, C, AT, SCTA. And that's all 24 possibilities. Now, we didn't actually need to write them out, but it is worthwhile to see that we can do it. Now, it becomes more interesting, well, maybe actually less interesting, what if the word was instead food? And so the answer here is we're actually not going to get 24 different permutations because this O and this O look the same. If I think of, well, I should use colors here. Colors would be great. So I think of like one O as being red and one O as being black. So if that's one way of arranging it, where these are 4 different letters, black F, black O, red O, black D, then this word and this word technically look different or look the same, but are actually technically different. So, and that's gonna be true for all the things. So like if I do, like FODO and DO, or I could do, let's see, I could do FDOO or FDOO. Right, these 6 different combinations or permutations I have when I have the first letter being F, just like I have these 6 here when the first letter is C. Really, I only have 3 different looking things. I have this, this, and this, and these other ones are kind of repeats. And that's because these 2 O's are kind of interchangeable. So here's how we would count them. We'd say, okay, well, there are definitely 4 factorial ways of arranging the 4 letters, just like last time. Just like here, there were 4 factorials of arranging the letters C, A, T, and S. Here, there's 4 factorial ways of arranging the letters F, O, O, and D. But we don't care if it's black O first, red O second, or red O first, black O second, whenever you have the same sort of thing. So we're going to divide by 2 factorial. And that 2 factorial is representing the number of ways we can arrange just the O's in any word. If there's 2 O's, there are 2 factorial, which is equal to 2 ways of arranging them. So whether you've got FOOD or FOOD, there's 2 factorial different ways we can put the O's in there. Same thing here. If you've got FODO versus FODO, there are 2 factorial ways you can arrange the O's. Which ends up being 24 over 2, which is 12. It's kind of interesting. Let's look at one more example. Maybe one. Well, I feel like I wish I could think of a good word that had like 3 of the same letter and 2 not, but I can. There's a great word. How about the word mummy? The excellent movie with Brendan Fraser and what's her name, Rachel Weisz. Yeah, great movie. Recommend it highly. So in this case, there's going to be exactly, there are 5 factorial ways of organizing the 5 different letters divided by 3 factorial ways of ordering, I said organizing before, but ordering is more word, of ordering the letters M. And that's going to be, so although we could actually calculate each part, I don't really want to, because it's easier to do this. 5 factorial is 5 times 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. Those all cancel, and you get 5 times 4, which is 20. So there's really only 20 different ways we can arrange these letters so you get something different, right? So just to point out, if I start with M, there's 4 factorial ways I could arrange these 4 letters. You could do UMMY. You could do, and again, I'm gonna think of this as M1 and M2. You could do UM1 YM2. You could do, okay, this will be a little bit lengthy. Sorry here. I know I'm it's worthwhile. I know it's a little bit time killery, but it's good to see what's happening here. So we can do I picked U. I still need to deal with U. Sorry, U, and then we could do. Apologies. Brain. Sorry. M2, M1Y, or you could do M2, Y, M1, or you could do. Let's see. We could do then Y, M1, M2, or Y, M2, M1. And those are all the ways we can get something that starts with M and U. But look, this is the same as brain. That. So these match up. And this matches with that. And this matches with that. And then I could also start moving around this other M here, right? I could interchange these 2 M's or these 2 M's. So we are exactly dividing by the number of ways you can organize the M's. I don't want to write them all out because it gets to be a lot, but we definitely are getting 20 different ways of doing this, which is still not insignificant. So kind of the idea here is if you're arranging letters in a word, you have to take the total number of ways you can arrange them and divide by the number of ways you can permute the doubled up letters. So one more, 5D. What if our word was statistics? Well, let's see. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different, or not different, 10 total letters in it. So there are 10 factorial ways of arranging the letters. But some of them are going to look like repeats because there are 1, 2, 3 S's. So I need to divide by 3 factorial ways of ordering the S's. There are 1, 2, 3 T's. So that's divide by 3 factorial ways of rearranging the T's. And there is 1, 2 I's. I have to divide by 2 factorial ways of rearranging the 2 I's. So that's divided by the number of ways of permuting letters that occur more than once. Which again, we could simplify. I do think it's worth seeing how these things simplify because it's something we do a lot of, maybe not a lot, but some of them. So this would equal 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1 times 3 times 2 times 1 times 2 times 1. And then we start canceling. 3, 2, 1, 3, 2, 1. 2 times 2 is 4. And then if we got a 3 here, 6 divided by 3 gives me a 2. So I'm left with 10 times 9 times 8 times 7 times 5 times 2 is 10. And then we can calculate that. It's not lovely, but it's not terrible. 10 times 10 is 100. 9 times 8 is 72. Times 7. 7 times 72 is 504, I think. It's 490 plus 14, yeah. So it's 100 times 504, or 50,400. That's the total number of ways you could reorder these letters and get a different looking word each time. All right, questions so far? It's okay if you don't have questions, but I do want to give you an opportunity. I guess I could type in the chat, just in case you might not be hearing everything I'm saying. Any questions so far? Cool. So, one more example, and then we'll talk about a more general formula. In an art contest, there are 10 entries. How many ways can we award a first, second, and third prize? And I'm gonna compare this to a slightly different question in a minute here. So, well, I've got for first prize, and again, you can do this in any order. I'm just kind of picking an order that seems natural, but you could totally pick the third place first and the second place next and the first place last. But if there's 10 entries, there are 10 different people I could pick to be first place. But after I've chosen whoever's first place, then there's only 9 people left. And there are 9 people left to choose second place. And thirdly, after I pick first and second, there's only 8 people left to pick third place from. Now, again, you could phrase this a different way. You could say, well, James, I'm going to start with third place. There's 10 spots there, and then there's 9 spots there, and then there's 8 spots there. Or however, it's still going to be 10 times 9 times 8, which ends up being 720 different ways. Shortly, we will contrast that with how many ways can you pick the top 3 without actually ordering who is first, second, and third. So this leads us to kind of a general formula for permutations, which is the following. The number of permutations of, now be careful with the numbers here, k, well, the numbers of k objects chosen from a group of n objects. It should be noted that k should be less than or equal to n. Right? If you're choosing k things out of n things, k should be at most as many as n is the following. And there's a couple of different ways of writing this. Some books write it as P of NK. Some calculators write it as NPK, or they might be using a C instead of a K. It is equal to n factorial divided by n minus k factorial. So in that previous example, just to kind of see how the formula works, if I was permuting, in the previous example, I'm permuting 3 people out of 10 people. Right, so my 3 is my k, my 10 is my n, and we get permutations of 3 from 10, and that's going to be 10 factorial over 10 minus 3 factorial, which is exactly 10 factorial, so 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, divided by 10 minus 3 is 7 factorial. And the whole, well, not the whole point, but the thing to see here, oops, sorry, you can't see that, apologies. Sorry, I keep getting off here. The thing to see there is that you don't want to actually multiply at 10 factorial, although you could. But the point is, you can see that the 7 cancel, the 6s cancel, everything down, cancel, and you're just left with 10 times 9 times 8, which is equal to 720. Or another example could be, we have to make a security code. And we have to form it by using 4 different letters. Followed by 3 different digits. How many codes are possible? And to be honest, I don't typically actually use that formula thing. What I would really probably do here, since it's a relatively small question, be like, okay, well, I need 1, 2, 3, 4 letters, 4 different letters, and 1, 2, 3 different digits. So I would say, okay, well, for the letters, there are first 26 choices, then 25, because I picked one and they all have to be different, and then 24, and then 23. And for the digits, there are first 10 choices, 0 through 9. And then after I've chosen one of them, there's 9 choices. And then after I've chosen 2 of them, there's 8 choices. That's how I'd probably actually do it. But if we wanted to use the formula, it would be equal to P of 26, permuting 4 things out of 26 times permuting 3 things out of 10, which is going to be 26 factorial over 26 minus 4 factorial times 10 factorial over 10 minus 3 factorial. And I don't have a calculator. Oh, actually, that's not true. I have a calculator. It's not mine. Looking to see if it has these buttons on it. It might. So if you have a calculator, you might be able to actually do these things. So let's just take a look here. If you look at, I think at either data, nope, here, nope, okay, or stat maybe, nope. Maybe not on this calculator. I was hopeful. I don't think I see the things I'm looking for. But if you have a calculator that has like a button that looks like an NPR like that, or an NCR, that's a different function. If you see those things in the calculator, you can calculate these things without having to write it all out, which is nice. I'm happy to show you how to make it work, but it's pretty straightforward. Yeah, really. Oh wait, I found it. It's on this calculator. There it is right there. So I hit the probability button, and then so if I want to do, it's got the NPR, the NCR, and the factorial right there, and some other stuff I don't care about. If I want to do this thing here, well, so you actually have to start by putting your number first. So let's just do the one we already did. Let's do 10 NPR 3. It should give us 720, which you already calculated. And it does. So that's 720. We can do the other one. We can do 26 NPR 4. And that should give us 26 times 25 times 24 times 23, which should be in the neighborhood of 36,000. Oh, sorry, 360,000. Apologies, I'm off by a little bit there. But that's, yeah, 358,800. And then we can multiply this together. Whoops, like that. And get approximately, not approximately, exactly. Let's see. I'm trying to say the words. 258,336,000 possible codes. So definitely useful to know where those buttons are on your calculator if you have to calculate these kind of things. All right, let's move along. So I'll emphasize one more time, permutations order matters. Combinations, on the other hand, order typically does not matter. Combinations. I know it's probably before your time. But whenever I hear combinations, all I can think about is that song, the combination Pizza Hut and Taco Bell. I'm at the Pizza Hut. I'm at the Taco Bell. I'm at the combination Pizza Hut and Taco Bell. Anyway, I know it's not really pertinent, but it's what I think of every time I think of combinations. So Pizza Hut, Taco Bell. Yeah. All right. Anyway, let's look at a different example first. So let's go back to our picking any 3 people out of 10. I don't care who's first, second, and third. I just want to know how many ways I can pick 3 people, and then later on I can decide who's first, second, and third. So, excuse me. Let's see here. I got 3 spots. And there are 10 choices for my first spot. There are 9 choices for my second spot, and there are 8 choices for my third spot. But I didn't actually care which order they came in. So here's what's happening. This is going to equal 720 permutations. That is too many, because here's what's happening with this. These 720 permutations are counting differently first, second, and third. Like, for example, it would calculate, let's say we have persons whose names start with the letters A, B, C through J. So we got A, B, C, D, E, F, G, H, I, and James. Let's say I picked persons D, E, and J. Well, I could have picked D first, E second, and J third. D first, J second, and E third. J first, E second, and D third. J first, D second, and E third. Not J, sorry. E first, D second, and J third, or E first, J second, and D third. And the problem is, if I'm counting this way with permutations, all of these 6 things are getting counted differently. But if I only care about how many ways I can pick 3 different groups of people, each of these is the same group of 3 people, just ordered differently. So if I only care about counting the number of different possible combinations, I'm going to take my 720 permutations and say that the number of combinations is equal to the number of permutations total divided by the number of ways of permuting the people I picked. In other words, in this particular example, it's going to be 10 factorial divided by, sorry, let's make this less complicated. It's going to be 720 divided by 3 factorial, the number of ways I can permute these 3 people, which is 720 divided by 6, which is 120. So there's only 120 different ways I can group any 3 people from these 10 people. Whereas then once I pick the specific group of 3 people, there are 6 different ways I can order those 3 people to decide who is first, second, and third, or first, second, and third, or first, second, and third. So hopefully that makes it a little bit more clear about what's going on here. So combinations order does not matter. Let's look at another example, but do definitely stop me if you have questions or chime in if you have questions. Let's look at an easier example. How many combinations of 2 letters out of 5 are there? Well, let's pick letters A, B, C, D, E. We can probably write them all down. In fact, there's a pretty easy way to write them all down. I can do A and B, or A and C, or A and D, or A and D. And I've done all the ways A can be with something else. Right? I'm making the implicit assumption here that I can't pick A and A, right? Because A and D are like 2 different. A is its own thing. Once I've picked it, it is picked. And then I could do, let's see, A, B, A, C, A, D, A, E. Yep. I could do B and C, B and D, B and E. Okay, B is spent. B has been combined with every other possible choice. Then I can do C and D, C and E, or finally D and E. And altogether, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 total combinations. Versus if I want to know the number of permutations of 2, about the permutations of 2 letters out of 5. We could write them all down, or we could look at what we've already written down and just say, well, you can either have all those or switch the order of any of them, right? I could have, I'm going to write them all down because I feel like I should. But you could have these 10. Or these other 10. BA, CA, DA, EA, CB, DB, EB, DC, EC, ED. So there are 20 permutations. Not terribly surprising, because if we do the permutation calculation, P of 5 comma 2, that's just 5 factorial over 5 minus 3 factorial, sorry, 5 minus 2 factorial, which is 5 times 4 times 3 times 2 times 1, over 5 minus 2 is 3. 3 factorial is 3 times 2 times 1. Cancel, 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 cancel. You get 5 times 4, which is 20. So the number of combinations of some number of things out of some other number of things is the same as the number of permutations, except you're going to take the number of permutations and divide by the number of ways of permuting the number of things you picked. In other words, what we're going to get here is we're going to get that the number of combinations, which we could write as C of 5 comma 2, is going to equal the number of permutations divided by 2 factorial. Which is 20 divided by 2. Or more generally, the number, and this is definitely an important formula, of combinations of pizza and Taco Bell. I hope I don't sound like a crazy person talking about pizza and Taco Bell here. If you haven't heard it, it's not worth listening to, but you should still go listen to it. It's very silly and definitely gets stuck in your head. So the number of combinations of K objects chosen from N objects is given by the following. And it's written a couple different ways. You can either write it as C of N comma K or NCK, or some calculators use NCR. They use R instead of K, but it's the same idea. I've also seen this notation, but here is the notation that's preferred by mathematicians. So this is the notation you will probably see in class, is N choose K. And we definitely do read it as, all these are read as N choose K. And it's just written as a big parentheses with an N over a K, but there's no like fraction symbol. It's just N on top, K on the bottom, parentheses around it. This is going to equal the number of permutations divided by the number of ways of ordering the number of things you're picking, K factorial. But the formula breaks down to being N factorial over N minus K factorial times K factorial. And the way I always think about it is you're going to have some N factorial on top, and then the two factorials on the bottom. The numbers that you're taking the factorials of should both add up to whatever that number is up there. So for example, to kind of see that previous example again, if I was trying to find 5 choose 2, it would be 5 factorial over 5 minus 2 factorial times 2 factorial. But really, I would jump straight to saying, oh, it's 5 factorial over 2 factorial times 3 factorial. I know I switched the order there, but that's usually because I look at that first and I'm like, oh, I do that factorial and then whatever the difference between 5 and 2 factorial is. And that's going to be 5 times 4 times 3 times 2 times 1 over 2 times 1 times 3 times 2 times 1. Cancel, 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 cancel. And you get 20 over 2, which is 10. So the number of ways of choosing K things out of N things where we don't care about the order, we just care about the number of ways you can choose them, is exactly N choose K, which is N factorial divided by K factorial times N minus K factorial. It's a pretty famous formula. It comes up all the time in different places in math. Oops. So then you get, so this is the formula we use a lot for like card questions. Yeah, for a lot of poker questions. So let's look at something like this. And the questions might seem kind of basic at first. So how, I need more paper, fine. How many ways can we form a committee where it doesn't matter what order you're picking them in, because right, you just want to have some number of people and we don't care, like there's no like president, vice president, treasurer, or anything like that. We just want a committee of 3 people from a group of 7. So maybe you're like in a group project and there's 7 of you in this group project. It was way too many for a group project, but you have to select 3 people to maybe present to the class. And so we want to know how many different ways we select a group of 3 out of the 7 people who are doing this project. So the answer is going to be 7 choose 3, which I really, I mean, I would ask you if your professors talked about this, which way he is saying it in, but if he hasn't given a specific way of doing it, this way of writing it, 7 choose 3, this is usually the best way, or at least the way that most mathematicians will default to. But if he's doing something else, let me know and I will do that. And then we're just going to calculate it. It's going to be 7 factorial over 4 factorial times 3 factorial. I would usually write the 3 factorial first, but I started writing it 4. The nice thing about this is you can always, now if the numbers get really big, you should just leave it like this. But for relatively small numbers, we can usually simplify this without too much effort. So simplifying this, here's what I'm really going to do. I'm going to go 7 times 6 times 5 times the 4 times 3 times 2 times 1 is just 4 factorial over 3 factorial times 4 factorial. I changed the order. And I can cancel those because they're the same. They're both 24. And I'm left with 7 times 6 times 5 over 3 times 2 times 1 is also 6. Those cancel. So I'm left with 3 times 7 times 5, which is 35. Sorry, let me know if I'm off page. I apologize. I keep trying not to move over, but keep wanting to. So there are 35 ways we can pick 3 people out of this group of 7 people. I should say there are 35 distinct ways we can pick a group of 3 out of this group of 7. Now, there's a good follow-up question because sometimes these questions get more complicated than just how many ways can you pick? So many out of so many. So follow-up. What if there are 2 people in your group that absolutely hate each other and cannot be on the committee together? So what if there are 2 people who just can't work together, who cannot be on the committee together? Or maybe they don't hate each other. Maybe they're so in love with each other that they just can't focus on the work they're trying to do when they're on the committee together. So we have to keep them separated because they're too in love. So there's a couple of different ways of going about this. And this is where the problems kind of get interesting because you have to kind of be very thoughtful about how you're going to approach it. And sometimes the kind of favorite approaches are trying to kind of add up all the ways we can get what we want, or the alternative kind of style approach is taking everything that we have and subtracting the things that we don't want away from it. So let's call those 2 people A and B. So you've got A and B, and then let's call everybody else 1, 2, 3, 4, and 5, just to be very distinct. So we know from before that there are 35 ways that we can pick any 3 people. But now we don't want some of those combinations, right? We don't want any combination with A and B and either 1, 2, 3, 4, or 5. So there are 5 ways that A and B could serve on the committee together. Right? You could have A, B in person 1, A, B in person 2, A, B in person 3, A, B in person 4, A, B in person 5. Sorry, that's the 3. So of the 35 different ways of selecting 3 people to serve on this committee, 3 different people, there are 5 of them we don't want. So it looks like we want our 35 total ways minus the 5 ways that have A and B together for a total of 30 committees of 3 out of 7 people where A and B are not together. That's one way of doing it. There's another way of doing it though. Another way would be to say, well, let's do it this way. I'm going to find all the ways of selecting committees with just A. So remove B. Then I'm left with A, 1, 2, 3, 4, 5. And so if I want to select 3 from there, I'm going to get 6, choose 3 ways of doing it, which is going to give me 6 factorial over 3 factorial times 3 factorial, which is 6 times 5 times 4 times 3 factorial over 3 factorial times 3 factorial. Those cancel, and you're left with 6, and 3 factorial is also equal to 6, so I can cancel this 6 with that 6. So I'm left with 20. And then I'm going to also see the number of ways I can do it by removing just A. So then I'm left with B, 1, 2, 3, 4, 5, which is going to give me also 6, choose 3, which is going to also be 20. But it looks like I've counted too many, right? By kind of a lot. What's going on here? Well, the problem is when I've picked 6, choose 3 from here and 6, choose 3 from here, maybe I didn't pick A at all. Or maybe I picked from these 5, and same deal here, maybe I picked from this 5. So what I've accidentally done is I've counted all the ways of picking 3 from these 5 twice. So what I'm going to do is now I'm going to say, well, I really only want to have done these 5, choose 3 one time. So I have to then subtract off. So definitely this is the harder way of doing it, I would say. But it is good to kind of see both ways. I want to subtract off all the ways of picking 3 from the 5 that can get along with each other, which is 5, choose 3. And 5, choose 3 is 5 factorial over 3 factorial times 2 factorial, which ends up being 5 times 4 over 2, which is 10. And so we've got 20 plus 20 minus 10. Oh, that's going to be 30, just like it was there. So either way works. It just, there's different ways of approaching problems like this. I think that's a pretty good stopping place, actually. Yeah, it is a good stopping place. So let's go ahead and stop there. I'll head over to drop or office hours in CADS, which I don't imagine either any of you will attend, but maybe you will. I don't actually know. You're certainly welcome to come over there if you want to, if you're on campus. Although I can see why you might avoid campus day because getting here on bus is challenging. Nothing. I don't know. Anyway, so have a lovely rest of your day. We'll continue talking about this stuff on Thursday. Definitely, if you have specific things you want to see on Thursday, let me know and I will try to make it happen. But yeah, the rest, and I will also point out the rest of the quarter is kind of just this. It's all chapter 12, probability, combinations, permutations, stuff like that. So all of the stuff we've been doing, although I imagine it'll probably show up on your final because it's probably cumulative. The rest of the class is kind of leaving all of that behind. You might inquire with your teacher what your final is going to look like. So you can either make sure you remember how to do the things we have learned already, or if they're not going to be on your final, you can go ahead and start forgetting them because you don't have to remember them. So I would encourage you all to check in with your teacher and see what the landscape looks like for the rest of the class. And then to let me know. All right. Have a lovely day. I'm going to end the Zoom and I will see you all, or not see you, but interact with you all on Tuesday.